Patty DeMute. I'm part of the architectural team at USG. This presentation is titled Today's Educational Facilities, Designing with Our Ears. Today's CEU will explore the following topics: the history of education architecture, the built environment, influences in educational spaces, designing with our ears, architectural acoustics, spatial and acoustical design in today's educational facility. How do we improve acoustics in the learned environment? Product solutions to acoustical challenges in educational spaces. COVID-19. Boston Latin School is in Boston, Massachusetts. It is the oldest public school in America. It was founded on April 23, 1635. It was modeled after the Free Grammar School in Boston, England, in which Latin and Greek were taught. The school was publicly funded. Believe it or not, 5 out of the 56 signers of the U.S. Constitution attended Boston Latin School. Horace Mann, often called the father of the Common School, began his career as a lawyer and legislator. When he was elected to act as secretary of the newly created Massachusetts Board of Education in 1837, he used his position to enact major educational reform. Credit for our modern version of the school usually goes to Horace Mann. He set forth his vision for a system of professional teachers who would teach students an organized curriculum. With the rising school-age population and stricter child labor laws, many urban centers required bigger school buildings to meet the surge in enrollment. In the United States, early classroom designs tended to feature stately neoclassical facades and standardized utilitarian classrooms with multiple rows of desks. Daylighting and natural ventilation were fundamental to many of these plans. Some designers also emphasized the importance of views so that students could rest their eyes at times. In Europe, the first open-air schools, such as Waldschule or Forest School in Germany, were aimed at stopping the spread of tuberculosis through exposure to air and sunshine. Classes were often held outdoors or in small buildings with folding glass doors, while the architecture of some larger buildings mimicked that of hospitals, reinforced by the notion of hygienic architecture. Beginning in the 1920s, leading architects began to lend their vision to schoolroom designs, including giants such as Eero Saarinen. These progressive schools began to be grouped together as examples of the open-air school movement. Collectively, they were characterized by their emphasis on fresh air, daylight, outdoor learning, and an easy flow through structures that might aid students' physical health and mental well-being. In the 1930s, intervention of Public Works Administration in the United States allowed school construction to continue despite the nation's financial woes, and many features of earlier schools were retained, if simplified. By the late 1930s, fluorescent lights and better ventilation had begun to appear in some schools. Post-war schools featured more standardized and cost-conscious designs, in part due to tight budgets amid the baby boom spike in school enrollments. One style that became popular in California and other warm climates was the finger plan design, which followed the era's more modern, one-story, flat-roof design aesthetic. Finger-like corridors gave each of the school's classroom maximum access to fresh air, daylight, and the outside. Across the U.S., air conditioning also debuted in schools, and ventilation standards became stricter. Although artificial lights were installed, most schools still provided plenty of natural light. This style marks the transition away from an imposing scale, formal architecture, and rigid organization of classroom cells within 2- or 3-story buildings. Dwindling enrollments and budgets in many school districts forced schools to economize or reconfigure existing spaces wherever they could. The 1960s also brought a greater emphasis on prefabrication techniques to the school construction industry and an increasing reliance on technology, which de-emphasized the need for large windows and natural ventilation. After the energy crisis of 1973, some schools replaced all of their large windows and natural ventilation with fluorescent lights and mechanical ventilation systems. The age of experimentation also led to open plan classrooms, which often lacked windows and suffered from poor acoustics. The U.S. Department of Defense also proposed underground classrooms, which could double as fallout shelters. Growth of the school population continued, and prefabrication buildings were added to campuses to temporarily accommodate enrollment. This movement began in Europe in response to a post-World War II rise in illnesses. This situation was attributed to faulty construction practices. The biology building placed an emphasis on buildings that were both healthy and environmentally friendly. This approach called for eliminating as many pollutants as possible from the building and a better focus on air, light, and acoustics. As a backlash to the experimentation of preceding decades, designs and renovations of the 1980s emphasized more modest investments and traditional features. By the mid-1990s, the U.S. officials had begun to note a state of disrepair affecting the nation's schools. Portable classrooms also began receiving greater scrutiny upon the realization that most of these structures were more permanent additions rather than temporary solutions. The debut of LEED spurred an emphasis on environmentally friendly buildings that also improved indoor air, light, and sound. Features such as low or no VOC paint and finishes became increasingly common, along with a renewed interest in better natural ventilation, daylight, and acoustics. So how do we go about designing classrooms to be healthier and more supportive of better learning outcomes? This is a question that perhaps is more important than ever. What a tremendous opportunity this is for both architects and educators to rethink what an educational facility should be and how the physical environment can be designed to have a positive impact on learning. There are many things about the built and natural environments that can impact school learning, with some researchers suggesting that 10 to 15% of variance in academic outcomes is influenced by the environment. The many factors that make up classroom design have been studied for their influence on learning. Factors that can interfere the most are temperature, seating arrangement, and noise. A review of studies investigating the relationship of temperature and learning outcomes reveal ideal thermal ranges for optimal learning are between 68 and 74 degrees, with about 50% humidity. The best seating arrangement should be determined by matching it with the task at hand. More interactive tasks benefit more from interactive arrangements, like semicircles and clusters, and independent tasks from independent arrangements like row seating. Noise has been shown to profoundly impact reading, writing, and comprehension skill learning, as well as overall academic performance. It is time to start designing for our ears. Architects and designers tend to focus exclusively on their eyes. They use them to design with, and they design for them. That is why our children end up sitting in their classrooms and in cafeterias that are so noisy that they can't hear their neighbor without shouting. We are designing environments that are making us crazy. And it's not just the quality of life that suffers. It is our health, social behavior, and productivity. How does this work? How do we create good sound environments? Let's begin with talking about ambience, our surroundings. Sound affects us physiologically, cognitively, psychologically, and behaviorally. All of the time, sound is affecting us. It is all around us, even though we may not be conscious of it. Communication requires sending and receiving. I can send effectively, and you can be a great listener, but if the space is not effective, that communication can't happen. The next concept we need to talk about is interference, those elements within our surroundings that make it more challenging for the student to hear the teacher. Open plan classroom design presents profound sound challenges. Unfortunately, some schools in the past decade have been built like corporate headquarters with vast central atriums and classrooms leading off of it with no back walls at all. In this example, children could not hear their teachers. This school had to go back in and spend almost $800,000 putting the walls back in. It is not just these modern buildings that suffer. Old-fashioned classrooms suffer too. Studies show that if you are sitting where the photograph was taken, row 4, speech intelligibility is just 50%. Children are losing 1 word in 2. Students have to work very hard to connect the dots to understand what is going on. Let's talk about those with hearing impairments. That is not just deaf children. That could be any child who has a cold, ear infection, or hay fever. On any given day, 1 in 8 children fall into that group. Then you have children for whom English is a second language. In the United States, that is almost 25% of the population. And finally, we can examine personality types. Introverts perform poorly when in a noisy environment like group work tasks. Think about the amount of children today whose education is being negatively affected by sound. These organizations all provide designers with acoustical performance criteria for schools. These standards serve as a basis for good acoustic design for any educational facility. Architectural acoustics. What is it? It is the science of controlling sound within a building. Architects and designers use single-rated testing methods to analyze the materials specified in the space for their ability to absorb and block different types of sound. As sound energy travels in space, it is reflected or absorbed as it interacts with all the elements in the room, with walls, floors, ceiling surfaces, furniture, and other elements in the room, including humans. Reverberation is the persistence of sound energy within a space due to ongoing reflections. It is a function of room size and the amount of sound absorptive materials present in the room. When interior surfaces are dominated by hard, sound-reflective materials, sound energy will persist and build up within a space, resulting in uncomfortable, noisy environments. Sound absorptive material will reduce reverberation, limiting the buildup of noise and improve acoustical comfort. Reverberation is the time it takes for reflected sound to die by 60 decibels from the original sound signal. Reflected sound builds up louder than the direct sound and makes it harder to hear. The maximum allowable reverberation time for classrooms is 0.60 seconds. Ambience or background noise is the totality of all sounds within a room when the room is unoccupied. The lower the ambient noise, the easier it will be to hear the teacher. The maximum allowable background noise for classrooms is separated into 2 parts. The first is noise from exterior sources like highways. The second from interior noises like HVAC equipment and student interactions. The maximum allowable background noise is 35 decibels for spaces under 20,000 square feet. This standard was set by ANSI. Signal-to-noise ratio is the sound level at the listener's ear above the background noise level. For example, students' main focus is on a signal, the teacher, but during transmission, it gets affected by noise, likely student interactions. This measurement is used to compare the level of sound attributed to the signal to the level of the background noise. The desired outcome is to ensure that the signal of interest, the teacher's voice, is louder than the background noise, pupils in the classroom. We have talked about sound. Now, how do we examine materials for their ability to absorb and block sound? The first of the testing methods we are going to discuss is NRC, Noise Reduction Coefficient. NRC examines a material's ability to absorb sound. Sound should be absorbed when the goal is to keep sounds within a room from reverberating or echoing. If a room has hard surfaces that reflect sound, it will take a long time for the sound to diminish. This is most noticeable in an empty room with hard walls, floors, and ceilings. You can actually hear sound bouncing around the room. Installing sound-absorbing materials such as carpet, acoustical ceiling tiles, or fabric-covered panels, it will reduce the reverberation by absorbing the sound. NRC is a single-rated system. A material with an NRC of 0 theoretically means that it completely reflects sound. A material with an NRC of 1 will theoretically absorb all sound. An acoustical NRC rating is at least 0.50. What is STC? Sound transmission class is a rating of how well a building's partition blocks airborne sound. Transmission loss is a measurement of the decibel difference on either side of a wall. Let's say we have a 100 decibel tone on one side of the wall, pretty loud. We measure this same tone on the other side of the wall, and we have 55 decibels. So we would say that we have 45 decibel transmission loss. Years ago, the walls in our schools were built with concrete block, so sound transfer was not an issue. Today, school walls are constructed with metal studs and drywall. ANSI has set the minimum STC of a wall separating two spaces at 50. Here you can see what can be heard with that 0.50 specification. Loud sounds are faintly heard. CAC, Ceiling Attenuation Class. This test examines a material's ability to block sound. Many walls stop at the suspended ceiling rather than extending to the deck of the floor above. As a result, noise from the adjacent space can move through the ceiling to the adjoining room. To reduce this type of noise, acoustical ceiling tiles will address this situation. High CAC values indicate higher levels of sound insulation between rooms. An acoustical CAC rating is at least 35. School acoustics usually brings to mind the ability or inability of students to understand their teachers inside the classroom. While this is important, schools have a variety of space types and desired acoustical experiences. In addition to the classroom, schools have gyms, auditoriums, cafeterias, media centers, offices, broadcast studios, industrial shops, weight rooms, and band rooms. The list is long. Treating every space like a classroom limits the acoustical excellence and the kind of experience that should be created in each of these varied spaces. There is an intimate relationship between room size, room shape, finishes, acoustics, and core function. An advisable approach is to use the acoustical purpose of a room to drive its aesthetic design. The alternative is to ignore these relationships and then struggle to address acoustics without negatively impacting the visual design intent. The former approach tends to result in a more fluid and linear design process and ultimately a highly successful experience inside the room. The latter tends to result in multiple design iterations, sacrifices, and compromised acoustics. The primary function of the room can be described in three categories: speech, comfort, and music. Thousands of students on any given day are unable to understand 25 to 30% of what is said in their classroom. Why is that? Excessive noise and reverberation. In the typical classroom, noise levels average about 65 decibels, a threshold for serious health damage with long-term exposure. For students, that leads to lower academic performance, and for teachers, it leads to a loss of voice, having to talk louder to be heard. The health implications are a higher risk of heart attack. Rooms for speech inside an educational facility can vary in size and function, from a room with 10 seats to an 1,000-seat theater. The primary acoustic goal in each is high speech intelligibility. This means that the listener can hear the speaker and understand what is being said. It also relates to the feeling connected to the speaker. This is called acoustical intimacy. In the classroom, this means a longer attention span. A well-designed speech room can hold the listener's attention even as the speaker turns away or is blocked from the direct line of sight and sound. Ideally, speech rooms should be as small as possible with low ceilings and sound-absorptive materials that decrease reverberation times. Classroom acoustics are important, but often a neglected aspect of the learning environment. Up to 60% of classroom activities involve speech between the teacher and the student or between the students. In a classroom with reverberation times of 1.2 seconds, which is pretty common, there is a tremendous echo. British acoustician Adrian James conducted an experiment. If you take that 1.2 seconds down to 0.4 seconds using sound-absorbing materials, the echoing is substantially diminished, allowing the student to easily make out what the teacher is saying. Smart classrooms are technology-based enhanced classrooms. Smart classrooms integrate new learning technologies. The existence of such devices inside a smart classroom increases the overall background noise by 10 decibels. Rooms for music instruction and performance are the most critical and challenging from an acoustics perspective. The primary acoustics goal is to make the music clear, full, loud, enveloping, and enjoyable. The problem is, unless the facility is a music college, there is usually only a few music performance areas, and those are usually multi-purpose in nature. The proportions and shape of a music room tend to affect reverberation times. Music rooms tend to be larger than a speech room. The increased size is necessary so that the music is fuller, louder, and enveloping. It is always advisable to hire an acoustic expert for these projects. Acoustic goals for the comfort rooms can be wide-ranging, from quiet relaxation to areas of individual concentration. Rooms include common areas, corridors, computer labs, cafeterias, weight rooms, gymnasiums, media centers, offices, and more. Comfort rooms vary in size and shape, but require a large amount of high-performing sound absorption overhead. Excessively loud and reverberant spaces are stressful and negatively affect concentration and productivity. Acoustic comfort, however, does not mean that these spaces are silent. In fact, silence can be uncomfortable. The goal here is to provide a lot of sound absorptive materials and a high level background noise. If the room is oversized, these spaces are not loud enough to energize the room. Background noise in this space include music, nature sounds, and electronic masking. Ceiling products have an immediate and high impact on the noise levels amidst all other elements of the built environment. The design community needs to design knowing something about the nature of the noise in the room, its intensity, sources, and effects. Once that is identified and quantified, you can then make recommendations as to how to address challenges. Evaluating a classroom is not as intimidating as one might think. Guidelines and an understanding of the products available today can help ensure sound control in educational spaces. Each of the spaces in our school have different needs. Acoustic product solutions include performance selectors and need to be considered specific to each environment. Acoustical ceiling tiles can have a dramatic improvement on classroom noise levels. These absorb more sound than standard ceiling tiles, which means they reduce sound reverberation in the classroom. Conventional plaster is highly durable and abuse resistant, a monolithic surface, high CAC and STC performance. Drywall, high CAC, low NRC, naturally fire resistant, sustainable, and there are abuse and impact resistant options. Monolithic acoustical drywall, high NRC and CAC, aesthetics with no exposed grid, unlimited shapes and sizes, similar installation as drywall, economical sound control. Perforated gypsum, lay-in or direct mount, high NRC, field painting allows for unlimited color options and different texture options. Glass fiber, high sound absorption, larger plank sizes, fine texture, washable and scrubbable surface, warranted against sag, mold, and mildew. Wet felted mineral fiber, dense, continuous process, mechanical perforations, a thickness of 5/8, 3/4, and 7/8, acoustical, VOC emissions are low, recycled content, economical, low maintenance, and fire performance. Cast panels, abuse resistant, acoustical, VOC emissions, fire performance, recycled content, higher cost, low maintenance, fire performance. Metal baffle, open plenum system, multiple shapes and spacing options, good acoustical performance with perforation insulation infill. Decorative clouds, metal or ACT, multiple shapes and configurations with an open plenum. It can be suspended below other ceilings. Wood can be lay-in, linear, or grills. It has the look of natural wood. Acoustical options are available. It's a higher cost product. Wood wool panels, lay-in or direct mount, wall or ceiling, high NRC. Field painting allows for unlimited color options. Different texture options are also available. Metal. Lay-in, snap-in, torsion spring. Clean look, multiple colors, wood finish options, and perforation options. It is a comparable NRC to ACT with acoustical insulation backer. It's a higher cost product. The COVID classroom. How has COVID affected how we specify material? In an effort to control the virus, the addition of plexiglass is common. This means there are more hard surfaces in the room, leading to an elevated echoing and reverberated space. State-of-the-art air purification systems to promote a healthier environment. This means that there will be additional mechanicals in the space above the ceiling, contributing to the noise level in the space. With a mandate to social distance, classrooms in the future will likely incorporate design changes like wider walkways and larger classrooms. There will be a particular emphasis on materials that can be effectively cleaned. Education design must consider incorporating materials that stand up to the cleaning that is now a mainstay. It is not unlikely that educational facilities could make a healthcare tile a mainstay specification. dedicated to helping you design with sound in mind. Join the conversation at usg.com/acoustics. This concludes the AIA presentation